Hello, I'm Keisuke Inomata, a postdoc at Johns Hopkins University. In this talk, I'm going to talk about my recent work with Leah Jenks and Mark Kamyakovsky. Okay, first, let me mention the main message of this talk. Chiral gravitational waves cause parity violation in observed four-point correlation function of galaxy distributions mapped onto 2D plane through lensing. So this is the main message of this talk. And please note that this signal does not explain the three-dimensional parity-violating signals which are reported for large-scale structures. Okay, so let me begin with physics. First, motivation. The parity violation in four-point correlation function is one of the hottest topics in cosmology. For example, in large-scale structures, 3 sigma detection of parity violation has been reported in these papers. On the other hand, in CMB anisotropies, there's no detection of the parity violations reported. In this talk, I'm going to discuss the four-point correlation function as a probe of parity-breaking chiral gravitational waves. First, let me explain what chiral gravitational waves are. This is a line element, and Hij is the tensor perturbation. Tensor perturbation can be expanded with the plus and cross modes as this, and right-handed and left-handed tensor perturbations can be made with a linear combination with the plus and cross modes. And we define the power spectrum of the right-handed and the left-handed tensor perturbations. And I'm going to focus on the case where the power spectrum of right and left-handed tensor perturbations are different. So this kind of gravitational wave is called chiral gravitational waves. Chiral gravitational waves can originate from the Chern-Simons term or axion-gauge coupling. And if Chern-Simons term exists, then the propagation of gravitational wave becomes chiral, then chiral gravitational waves are produced. If the axion-gauge coupling exists, chiral gauge fields are produced. Then chiral gauge field produce chiral gravitational waves. So this is how chiral gravitational waves are produced. Now let me explain what lensing is. If gravitational waves pass between the observer and the galaxies, the apparent position is shifted from the physical position here. So this is a lensing, and the lensing can be characterized by 2 parameters, phi and omega, as this, and this part is the curl-free component, and this part is curl component. Observed galaxy number density field is given by this, and delta Z0 is the density field before lensing. Okay, so this is a setup. We consider a far cubic observation value, and we neglect the redshift dependence of the lensing effects. Then the Fourier discrete modes are given by this. So from these expressions, we can obtain the Fourier modes as this. And theta is defined as this. Okay, so now let me explain the 2-point correlation functions. And 2-point function in the existence of deflection field can be expressed as this. First term is the galaxy number density per spectrum in the absence of the deflection field. And the second term is the power spectrum in the existence of phi and omega. So we can see that the phi and omega dependence here. And 4-point connected function is given by this. Point is that under parity inversion, the dot product is invariant while the cross products change sign. So this means that this term, the cross correlation term, is a parity odd in 4-point correlation function in 2 dimensions. Okay, let me explain what we observe. So this is the observed 2-dimensional galaxy map, and blue and red cone figures are connected under parity inversion. Then 4-point correlation function with a blue configuration is larger than the red one. So this is what we observe. Please note that the total system to 2-dimensional map plus observer is 3-dimension. This is why the parity violation signal appears in this setup. Please note that this parity violation signal is irrelevant to the ones reported in 3-dimensional data of large-scale structures. Okay, so we have seen that the cross-correlation term is the parity output in 4-point correlation function in 2 dimensions. So one might ask, is cross-correlation term related to the chiral gravitational waves? Answer is yes. In the flat sky limit, cross-correlation power spectrum can be expressed as this. We can see that this cross-correlation term comes from the difference between the left-handed power spectrum and right-handed power spectrum. And this is indeed non-zero for chiral gravitational waves. On the other hand, for the odd correlation power spectrum, that is expressed with the sum of left-handed and right-handed tensor power spectrum. So parity odd part comes from the chiral gravitational waves. Okay, so next, let me discuss the estimators in order to discuss the detectability of gravitational waves. We have seen that chirality of gravitational waves is imprinted in the cross-correlation power spectrum, P phi omega. And let us make the estimator of phi and omega to discuss the detectability. Let me recall the 2-point correlation function in the existence of phi and omega. From this, we can make the estimator for phi and omega as this, and f comes from these quantities. And we can see that under the exchange K1 perpendicular and K2 perpendicular, this f phi is symmetric. On the other hand, f omega is asymmetric. This comes from the fact that omega is the Carl mode in the 2-dimensional celestial space. So that's why f omega is asymmetric under this exchange. The variance of these estimators is given by this. And since this estimator is the estimator of X with one pair of K1 and K2, we sum it over all pairs of K1 and K2 with inverse variance weighting as this. And P tot is equal to PZ, galaxy number density power spectrum, plus PM, which is the noise power spectrum. And this is determined by measurement. Okay, so here, to be concrete, let us consider a simple chiral gravitational wave spectrum. So we consider fully chiral gravitational waves, where the there is no right-handed gravitational waves. So all gravitational waves are right-handed. And we defined L as this, and the PFL is normalized as this. So we are interested in the detectability of L. Let me recall the cross-correlation power spectrum, which can be expressed as this. And from this expression, we can obtain the estimator of Al as this. And similarly, the variance is given by this. And summing over all K modes with inverse variance weighting, we finally obtain the estimator of Al. And the variance is given by this. The point is that if the gravitational wave amplitude satisfies this inequality, then we can detect the gravitational waves. So if the amplitude is larger than this variance, then we can detect gravitational waves. Okay, so here, let me mention the number of modes considered. A finite observation volume leads to discrete K modes instead of continuous K modes. And the smallest K is determined by the box size as this, and the largest K is determined by the measurement resolution. The number of modes is more than 1 for the smallest K, and the K max over K min for the largest K. So this is a number of modes considered. Okay, finally, let me explain the detectability. Again, these are estimator and this is the variance. And we assume a peaked power spectrum for gravitational power spectrum for simplicity. After some calculation, we finally obtain the order of the variance and the M function is this. And I skipped the intermediate calculation, but after some calculation, we obtain these order estimates. And let us here consider the case where the signal becomes the strongest within current constraints. Let me record the expression for the variance. And let me record that if AL is larger than sigma AL variance, then we can detect the gravitational waves. And the lower frequency gravitational waves lead to the smaller sigma AL, which can be seen from this factor. And the smaller sigma AL corresponds to easier detection. However, gravitational waves in this scale, in large scale, are constrained by CMB. Given this, we consider the gravitational wave spectrum with a peak in the non-constraint frequency as this. So we consider the gravitational waves like this. Then we obtain this result. This figure shows the relation between the variance and the Kmax R. The regions above black lines are the detectable regions. So note again, if AL is larger than sigma AL, we can detect the gravitational waves. And this dotted lines, horizontal dotted lines show the case with the AL equals 1. This corresponds to the perturbation limit. So this is the largest gravitational waves in the perturbation theory. And we can see that this line crosses the black solid line around the order 10 to the fourth. So this means that Kmax R must be larger than order 10 to the fourth for the detection of these maximum gravitational waves. Let me here substitute some concrete values. R equals 7 gigaparsec, which corresponds to redshift equals 4, and the K min R is 10. Then we find that this condition corresponds to this condition. So this means that in order to detect the maximum gravitational waves, we need to measure the density fluctuations whose scale is smaller than 1 megaparsec. Unfortunately, galaxy surveys cannot reach this scale max because the typical distance between galaxies are order megaparsec. However, 21 centimeter or other line intensity mapping could possibly do that in the future. Okay, let me summarize my talk. Chiral gravitational waves cause parity violation in observed 4-point correlation function mapped onto 2D plane through lensing. However, the signal is so weak that galaxy surveys could not detect it. Please note again that this signal does not explain the three-dimensional parity violation signals reported for large-scale structure. Okay, so I stop here. Thank you so much.